Okay, so if I take these, I can arrange them so that I get this. V is equal to V naught. Okay? And you can do the same if I'm talking about a flow system, right? What changes? All I have to do to go to a flow system is change the total volumes, big V's, to volumetric flow rates, and instead of moles, it's molar flow rates. All right, everybody see that conversion? So going back to, wait, do I have another one of these tables? I think I'm done with the tables. So that's for the flow systems, but let's stick with batch for a while, and then we're going to come back and talk more about flow. I just don't want you guys to get confused by switching between big V, little v every 5 minutes. Okay, so we have something that expresses volume, right? We want to express it as a function of conversion. Right now, it's not written in terms of conversion. Instead, it's written in terms of number of moles. So just like we did earlier, though, we have expressions to handle that. Nt over Nt0 is equal to 1 plus delta NaO over Nt0 times the conversion. Okay? You can also write it like this. What is YAO? Mole fraction, yeah. That's harkening back to the good old days, right? But yeah, mole fraction of A in the initial stream. And we're going to have another one of these little definitions. We're going to say for convenience, epsilon, all right, is equal to D over A. Okay, again, this is just a definition. And I can also write this as what? What is this thing in the parentheses? And what is that ratio of moles? Y. The mole fraction of A. Again, in the inlet, or initially. So in terms of words, what this is saying, it's a little bit different from delta, but this is saying the change in total number of moles divided by the total number of initial moles. And so this is just, there's only one of, ran out of room. At total conversion. So it's just a little bit different. Remember that delta was not at a specific conversion, right? Delta was simply defined by saying the change in the total number of moles for every 1 mole of A consumed. This is saying the change in the total number of moles at complete conversion, not divided by number of moles of A consumed, but just total number of moles in the inlet, or initial.
Can you give me a little example of that? I don't understand. The change in total number of moles.
So what's delta equal to?
So divided by
C over A.
Yeah, -1. Is it n minus beginning?
Just look at the formula. C over A, right, which is 1 over 2 minus what? 1 equals -1/2.
Oh, okay. Gotcha.
Now what's epsilon equal to? You see it depends on the number of moles that you start with, right? But the difference is that this isn't assuming complete conversion or anything like that. This is just based purely on the stoichiometry. This is saying that if you let this reaction carry out completely, how many moles disappear from the system per moles that you started with? So in this case, how many moles disappear compared to the number of moles that you started with?
That would be -1,
right? Because if you started with 2, at the end you're going to have 1 over 2. But yeah, here's your formulas. And so now, we're going to come back to this equation, where remember we had this in here and we wanted to get rid of it, right? We want to put it in terms of conversion. That's it. So again, epsilon's just there for convenience. It just makes that final form a little bit simpler. So now we had volume as a function of the number of moles, temperature, and pressure. Now we have volume as a function of the conversion, temperature, and pressure, which is what we wanted. And again, I can get a similar reaction for a flow system. Right? It's the same equation. The only thing that changed is that the volumes went from being the big V to a little v for volumetric flow rate. But epsilon's defined just slightly differently now. Right? You can define it in terms of flow rates, but you get right back to the same expression. Does everybody see how you can jump from batch to flow and not a lot's changing? What do you guys think we're going to assume for Z? Yeah, that ratio anyways is about 1. Or just saying that those are about equal. So that's going to drop out. You're not going to be expected to solve compressibility factors or anything like that. If you're asked on a homework or something, you're going to have to be provided the I'm not going to send you to compressibility charts. All right, what's another assumption that we're going to sort of often make about these systems? Is that they're isothermal. Remember, that's chapter 5, so that's where we're headed right after this. So what else cancels? Yeah, isothermal means that T is equal to T naught. So that drops out too. If I have a flow reactor open on both ends, would I expect the pressure to change? Not a lot. It's a bit of a trick question. You guys have had fluid flow by now, right? So you guys should know that the pressure is always changing, right? You're always going to have pressure loss across some flowing pipe. Especially if now I fill that pipe with a powder. Why would I fill a pipe with a powder and then run reagents over it? Catalysis. Yeah, so pressure drop can be a very important thing in reactions. But often you're going to be told, assume that the pressure drop is minimal. And if you're told minimal pressure drop, then that means that P is just about equal to the initial pressure. And that also goes away. So you get some pretty simple expressions at the end, right? For these limiting cases, volume as a function of conversion is simply equal to the initial volume times what? 1 plus epsilon x, yeah.
How can you say the same that P naught over P cancels out for a batch reactor? Like where you have solid rigid volume.
Yeah, you can't. This is everything
Yeah,
we've
but
been talking
that-
about.
You cross that out on that function where it says V equals V naught. The
I see
formula-
what you're saying. Yeah.
No, yeah.
Yeah, but I mean,
Okay, I was just
technically
like,
speaking, you can't have a batch reactor with constant pressure. It just can't be a rigid reactor. So the formula still works.
yeah.
But yeah, if you have a rigid system, then you're not at constant pressure.
Yeah.
So that's.
I just was making.
But I mean, you can be at constant pressure. That's again, it's a piston, right? Yeah, so that's our expression. And then for flow systems, the volumetric flow rate is just equal to the volumetric inlet flow rate, again, times 1 plus epsilon times the conversion. But no, you can't cross out P naught over P if you have a rigid batch reactor. Okay, so just some things to kind of remember. If that's greater than 0, what does that mean? Are we producing moles as we do the reaction or consuming them? Yeah. Right, the volume goes up. So the net number of moles produced is greater than the number of moles that you started with, right? And again, that can be something like A goes to 2B. Right? I'm making more moles than I'm consuming, because every time I consume 1A, I make 2Bs. And so that also means that the volume increases with increasing conversion, right? All right, so let's talk a bit more about.
Do you mean V is greater than V naught, not 0?
That's actually what I meant to write. But good catch, yeah. Volume increases. All right, so if I have a little plug of liquid or gas flowing through a system, sorry. So the number of moles is NT0, the volume is V0, right? And then that's true at a residence time of 0. What does a residence time of 0 mean physically?
It's instantaneously there and gone at the same time.
Yeah,
That's like in infinitely small section.
it's in the very front, right? Because at the very front of your reactor, in an infinitely small part of that reactor, yeah, the residence time would be essentially 0. So in other words, it's the inlet condition, okay? But then I go forward in time or along the reactor bed. So obviously, based on the way that I've drawn it, the volume has increased, right? That means that if it's an ideal gas, the number of moles have also increased. Yeah,
I forget what resonance time is. Can you remind me?
sure.
Is it the amount of time it spends there? or-
Yeah, yeah. So the residence time through an entire reactor is just the volume of the reactor divided by the volumetric flow rate. Right? So look at the units. You have
Yeah.
liters over, right, liters per second, so you end up with seconds. Now, you can also, though, talk about residence time as a function of the bed, right? Because just like time is a continuous function, right? Residence time is less if I have a tube, I can say that this residence time is equal to 0. This residence time is equal to that total residence time, total volume divided by volumetric flow rate. And in between, I have some fraction, right? It's how much volume have I experienced divided again by the volumetric flow rate.
So with an increase in volume, since it's a rigid pipe, well, you would have an increase in velocity, so it would move faster through the pipe, right?
Yeah, so that's what we're leading to, yeah.
So,
So, have I changed the mass?
so then if you increase the volume, it slows down.
No, what goes in goes out. There can't be accumulation inside the pipe.
Yeah, it's got to flow faster on a linear scale because you have to move more material through a larger region, right? Here I only have to move it this far. Here I have to move it further.
Oh, long. Oh, I thought you were talking about that.
No, because remember it's fixed in that direction.
No,
Yeah, because it's a pipe. So have I said anything about mass, right? Does the mass change?
If the
No.
density changes.
No.
No, mass balance. What goes in must go out.
Right. The mass is fixed in both of these. So, what changes? What happens to the density?
It decreases.
Yeah, I just want to double check.
If volume's increasing, the mass is
Yeah.
the same. It has to decrease.
Yeah. It's not like written in the notes for some reason. There's this whole thing about density, but he's got it hidden. But yeah, the density's got to decrease, right? Yeah.
But there's an increase in the number of moles directly proportional to the mass.
No, it's not. Why are moles proportional to mass? We're reacting things here.
Oh, okay.
Yeah, that used to be true. It is no longer. Okay. No, when you're doing reactions, number of moles is no longer proportional to the mass. Total moles, that is. All right, so again, we want to find volumetric flow rate as a function of conversion, right? And that is because what we actually want is to know how do we relate the concentration to all of the flow rates. All right, why am I forgetting how to draw an ampersand? I'll do it later. Because again, what we ultimately really want is concentration as a function of conversion. That's what we need to relate it to rate equations. Concentration as a function of conversion. So concentration for a flowing system is what? Is it number of moles or flow rate of moles?
It's fluid.
Flow rate. And then I write the wrong thing. Right, F over the volumetric flow rate. So again, we need this as a